First of all, please do make sure that the totals on your exam are correct. And if you have any problem with grading or any questions about grading, make a note of it and right after the class, return it to me. I'll be happy to look at it. Uh, very quickly, I'll go through the solutions and you can check along your work. So the first problem, let's see. The first problem was this cantilever beam with a varying cross-sectional area or a varying modulus of uh, bending modulus EI. Of course, I was missing the 1 over L factor out there, but again, it should not have affected your calculations except for a factor of L. So in any case, you should have been able to see that since the bending moment diagram is linear, going from minus FL to minus 2 FL, and the EI also goes from EI here to 2 EI here. And at the end, the curvature is constant throughout the length of the beam. And using the moment area method, you can almost in one step calculate the required deflection. But if you use the double integration method, you had to calculate those two constants. And what you should have gotten is FL cube over 2 EI. So hopefully not terribly complicated. I did notice that the most common sort of error was that maybe you did not realize how you were supposed to interpret this varying EI along the length. And you tried to use it as its value at x equal to a, or kept it as a xei over L on the left hand side, which you cannot do because it's a varying bending modulus along the length. So you need to integrate the entire curvature. This numerator is moment divided by the varying bending modulus, and it becomes constant. So the integration is real easy. Any questions on this? All right. Truss problem, almost exactly the same problem as on the sample quiz, except I moved the load from B to D, and as instead of asking displacement at D, I was asking you the displacement at B. Internal forces are very similar, -5 compression, 8. Instead of this being a 0 force member, it's a 8 here, 3 and 3 compression. Oh, sorry, 3 and 3 tension here. External work done is half times load times displacement. This is probably the most common error I saw, that some of you just said that this was going to be equal to delta B. It's definitely not delta B, because the work done is equal to the distance half times the load times the distance traveled by the point of application of the load. So it's delta D, not delta B. And if you did your calculations for internal energy correctly, then you should have been able to see that really what's happening is that the displacement at B is equal to the displacement at D minus whatever is the extension of BD, right? If BD is a 0 force member, like it was on your sample exam, it would have traveled as a rigid body without compressing or extending. In that case, delta D was equal to delta B. But in this case, since BD is being stretched by 8 kilonewtons, BD, the displacement of B will be slightly smaller than displacement of D, and happens to be 38 over AE. Okay, questions? All right, and the solutions, by the way, are posted on the Blackboard front web page, right where the sample quiz was posted. So you can take a look at it in more detail. And if you have any questions, let me know. This problem also, I think a few of you seem to have gotten confused. First of all, the deflected shape would kind of look like this. There is bending moment in both horizontal and vertical members. So if you apply the principle of real work, real energy, then the work done by the external force will be half times the load times the vertical distance it drops, right? We don't need to worry about the horizontal distance. And all of that external work is going to get converted into internal energy in both of those legs, not just horizontal or not just vertical. Okay. because this entire structure is acting like a spring, if you will. And all of the external work will store in all of the internal energy of the structure. Another thing I saw that was, maybe some of you mentioned that yes, indeed there would be a fixed end moment here, but since this is a fixed end, there is no rotation there, right? And if there is a reaction but no rotation at that reaction point of reaction, then the external work done is zero. I mean, you don't really have a half times m theta term in there. Okay, because of course, if you had theta, then you'd have two unknowns and you won't be able to calculate anyway, right? So in this case also, I think the calculations should not have been too tricky. External work done, internal energy stored. You just sum up the internal energy in both the legs and end up with that expression. Any questions on this? Okay. So I think maybe just a few thoughts after the quiz. I think most of you did very well. But if you feel that you could have done much better, there's still 3 more quizzes to go, lots of homework to go. There's a lot of, and the final exam, of course. There's a lot of room to make up. I might have mentioned maybe on some of your quizzes that please do feel free to come and talk to me if you feel that certain things are not clear. Um, and I'm sure you can do much better in the coming quizzes. Okay. All right. So what we'll do is go back to what we were discussing before last time really. I do have a couple of extra handouts from last time in case somebody needs one. And so very quickly, what we were talking about last time was this method of virtual work. We had already talked about trusses. We were talking about method of virtual work for beams, as opposed to the real work, real energy method that was on the quiz. And I told you that the idea is really very similar. If you want to evaluate the displacement or a rotation of a beam at some point, a beam or a frame at some point, you apply a virtual load P prime or a virtual moment M prime there. And essentially, the internal energy expression, well, first of all, the external work done expression is simply P prime times delta or M prime times theta. There's no half, of course, there, as we've talked about several times. The internal energy expression is always the bending moment due to virtual load times curvature due to real load, right? Red times blue. And we went through a couple of examples with that. I won't go through that example again. And this is about where we were last time. We were doing this as an in-class exercise. So just to complete this out, I'll go ahead and do that. The question simply says we have a cantilever beam with a uniformly distributed load, and we want to find the vertical displacement at B. So of course, what we'll do is apply for the virtual system. We're going to apply a virtual P prime at the point at which we want to calculate the displacement, and the bending moment diagram due to this virtual load would be something like minus P prime times L, and if I measure X from the right, then it's simply minus P prime times X, right? So I now have the real bending moment diagram and the virtual bending moment diagram. And just to be consistent, I'll draw the virtual bending moment diagram in red. So we know now that external work, virtual work done, WE prime, is equal to the virtual load P prime times the real displacement delta B that we are looking for. and ui prime is simply equal to the virtual bending moment, which is minus p prime times x, times the real curvature, which is minus omega x square over 2 ei, right? And we simply integrate that from 0 to L dx, which happens to be p prime omega 2 ei can come out, and we'll have x cube inside. The integral of x cube would be x4 over 4, 0 to L, which happens to be, of course, p prime omega L4 over 8 ei. And if I equate we prime to ui prime, then basically we get delta b is equal to p prime cancels off, and we get omega L4 divided by 8 ei. And you can plug in the numbers. L equal to, I believe, 10 meters. Omega is equal to 12 kilonewton per meter. And I think E and I are also given, but I'll leave that for you to do. Any questions on this? So it's very similar to the real work, real energy method, but again, much more powerful, much more general. You can find the displacement or rotation at any point in the beam, right? Let's take another example. This look familiar? So yes, indeed, this is the same frame. Now we are going to solve the same frame. Instead of real work, real energy, we're going to use virtual work, virtual energy method. We already know what the bending moment diagram looks like. I have the axial force diagram and the shear force diagram as well. We won't use that for now. We'll do that in a little bit. And since we want to find the vertical deflection at C, we are applying a vertical P prime load at C as well. If I wanted the horizontal displacement, could I use the real work, real energy method? I could not use the real work, real energy method for horizontal displacement, but I can indeed use the virtual work method. Just I apply a P prime horizontal, right? But let's see if this matches up with our answer from the quiz. So response to the virtual loads, if I apply a P prime here, what would be the bending moment diagram? Yep, exactly the same thing, except instead of 100, I'll have P prime times 20, right? So I take this response curve. So let me draw that here. And since this is a virtual bending moment diagram, I'll draw it in red. Same sort of variation. This value is negative P prime times 20. And this is again measuring x from the right. I can write it as minus P prime times x. So the virtual work done is once again P prime times delta C, and UI internal energy is in the horizontal leg going from 0 to 20, virtual bending moment minus P prime times x, and real curvature, that's minus 5x divided by EI and dx, and I need to add the vertical component plus 0 to 20 of virtual bending moment minus P prime times 20, real curvature, that would be minus 100 over EI dx, right? And If we calculate that out, the first term turns out to be 5p prime over EI. So we have x squared left in there, becomes L cube over 3. So that's 20 cube over 3, and plus we have 2000 p prime over EI, integral of x, that becomes simply 20. And I think if you equate WE prime to UI prime, you should get delta C as the same thing that we got for the quiz. Oh, not -4, +4. So again, the logic is similar, but conceptually very different between the real work and real energy and the virtual work, virtual energy method. Questions on this? Any of these methods? Okay. All right. So what we'll do next is look at a few different type of applications of the real work, real energy method. And this is really where, sorry, not the real work, but the virtual work method. But this is really where this method really is very advantageous over whatever structural analysis methods you learned back in 371. If you remember from 371, you always were using an assumption that shear deformations are negligible, right? Or axial deformations are negligible. You were only accounting for bending deformations. But the principle of virtual work is so general that as long as you can calculate the internal energy stored in a structure, you can apply it even to situations where the beam is not, where the beam does not have shear deformations negligible. So let me ask you this. If I have this beam, hopefully you can all discern that if I hold the beam this way and bend it, am I bending it against the strong axis or the weak axis? This is thinner, and if I flip it over like this, it's thicker. So if I bend it like this, is this the strong axis or the weak axis? Weak axis, of course, because I can, moment of inertia would be BD cubed over 12. D is smaller in this case, so I can bend it a lot, right? I can bend it a lot with the same amount of moment. And what that shows is that the bending deformations are quite large. Let me ask you this now. Are there any shear deformations in this beam? Are there shear deformations in this beam when I bend it along its weak axis? We do neglect them, but there are shear deformations, right? Shear deformations are, if you remember, I told you, if you look at these two cross sections, any two adjacent cross sections, if they behave in this way, if this is the kind of behavior sliding against each other, that's a shear deformation. And shear deformation is indeed always present. It just so happens that in such a, in this case, when we are bending it against a weak axis, shear deformations are extremely small. They are extremely small in comparison to the rather large bending deformations. So we neglect them usually. However, if I flip it like this and try to bend it now with the same amount of movement, it does not bend a whole lot. Right? The bending deformations are small. And in comparison to these small bending deformations, the shear deformations are not negligible. So that's why we do not neglect shear deformations for deep beams, because the bending deformations are not big enough for us to neglect shear deformations in comparison to. And that's what we'll talk about right now. So in terms of the other applications for the virtual work method, the idea is still exactly the same. We want to, if we want to find the displacement or rotation, we apply P prime or M prime. We've already talked about trusses and beam bending, so I won't go through that again. But this is what we were talking about just now. If I have a cantilever beam, tip load applied, if I'm looking only at the bending deformations, then you should be able to see that all of the cross sections essentially remain perpendicular to the center line, right? because we are assuming that there is no shear deformation. However, if the beam is a deep beam, then adjacent cross sections will indeed have shear acting between them, and what you will see is that these sections will slide against relative to each other, and the displacement would be a little bit more than what you had for the pure bending case. And to account for this, you cannot really use your moment area method or all of those methods from 371 because they assume that shear deformations are negligible. Here, we can account for this energy stored in the shear deformation mode, and using that energy stored, we can find the additional displacement due to shear. So let's see how that works. Internal energy is always virtual stress times real strain. This is something that we saw when we talked about the method of virtual work. And it's integrated over the volume of the body, right? dV. For beams, it just happens to be area of cross section times dx. So let me ask you this now. So for the shear case, when I apply, let's say, some load and I can draw the shear force diagram, it would just look constant, right? Go up by P, go across constant P, and drop down by P. So assuming that the shear force is constant along the beam, or even looking at a shear force at some cross section, I have this V as the shear force. V is the shear force that is acting on the entire cross section of two adjacent cross sections. Okay, so if I have a V, I have V as a shear force. What is the shear stress? We did that back in homework 1. VQ over IT, right? And since that's a little bit more complicated expression that we want here, we can make a crude approximation. We'll say that we'll assume this shear does not vary quadratically along the cross section. Instead, we'll assume it's a constant value, an average constant value across the cross section. And that shear stress would really just be V prime divided by area of cross section. Okay. And to account for the fact that it is not really a constant shear across the cross section, it is really a quadratic variation across the cross section, and which will of course depend upon the shape of the cross section. If it's a W-shaped beam versus a rectangular or a circular cross section, it would be, this shear stress would be different. So what people commonly do is to apply some sort of a fudge factor called kappa, where this kappa is the cross section shape factor. And usually it's very close to 1. So unless I give you the value of this cross section shape factor, just assume it to be 1. So this is the shear stress on the cross section. What would be the real shear strain? Shear strain. So this is virtual shear stress. The real shear strain would be shear force diagram V divided by area of cross section, same area of cross section A. That gives me real shear stress divided by G. Instead of dividing it by E, the Young's modulus, we divide it by G, the shear modulus, and that gives us shear strain. Okay, and then the rest is same A dx integral 0 to L. And that indeed is the internal energy stored in the shear deformation mode of any beam. Okay. Once again, even if I bend the beam in the weak axis, this is still the shear energy stored in the beam. But this shear energy stored would be very small in comparison to the bending energy stored in the beam. So we neglect it usually. However, in the deep bending case, we do not neglect it. And just for sake of simplicity, we can cancel off one of the A's. but I would rather have you actually write out the internal energy in this way: that shear stress times virtual shear stress times real shear strain times area times dx, and then of course one of the a's will cancel out, but at least this will help you understand the expression where it comes from and apply it correctly rather than having to memorize it blindly, right? Okay. Um, so this is the internal energy stored in the shear mode. And finally, there is one more mode for the beam deformations that we need to talk about, which is of course the axial mode. It's a beam, no doubt, but indeed if I apply an axial force, it will stretch or compress. And together with the together with the bending mode, shear mode, and axial mode, we have covered all the possible modes of deformation of the beam. As long as plane sections remain plane and actually rigid cross sections remain rigid, these three modes of deformation cover all the possible modes of the beam. Um, the axial deformation energy is very similar to what we've already seen for trusses, so I won't go into too much detail about this, but we'll go as usual. If I have a horizontal force n prime, virtual horizontal force n prime, the virtual axial stress would be n prime divided by a, very similar to the shear stress. Axial force divided by area of cross section, that's axial stress. We don't need a cross section shape factor in this case, because no matter what the cross section shape is, if I apply a constant or a horizontal this axial force, it will be uniformly distributed along the cross section. It does not distribute along the cross section in a quadratic manner, right? So the real axial strain would be n divided by a, which is the stress, and divided by e, that's the strain. Does n over ae sound familiar? It's very closely related to nl over ae, right? Why? Because nl over ae would be the expression we would get if we were to integrate it with dx, right? Integral of n over ea dx would be nl over ae, but we leave it as it is because for beams you might have an axial force in the middle of the beam, and then you would have to integrate from that point onwards. So axial force can change along the length of the beam, but in a truss member, the axial force does not change. So that's why we had NL over AE there, but we'll keep the integral here. So A dx integral 0 to L. And once again, we can cancel off one of the A's, but it's better to write it in this exact same manner. Okay. All right. So these are two additional modes of deformation. We'll talk about two more modes of deformation in a little bit, but let's see a very simple example with this. Cantilever beam, we want to find the vertical displacement, but now we are not neglecting shear. In the first case, we are using only bending energy. We already know how that works out, but the new one would be trying to find out the deformation of the tip of the cantilever when I don't neglect shear deformations. So in this case, I can neglect shear deformations. I'm bending along the weak axis. But if I flip it over and bend it like this, the bending energy is smaller, and the shear deformation energy is comparable to that, so we should not neglect it. So that's what we do. In both cases, what would be the external work done? If I want to find delta here, first of all, of course, I will apply P prime here as well. And in both cases, I'll get the same exact shear force and bending moment diagram, except replacing P with P prime, right? So what would be the external virtual work done by this P prime going through real delta? P prime times delta. It's always exactly the same. P prime virtual load times real displacement. That's always the external work done. And the internal virtual energy stored would be, for the bending case, we would have m prime, which would be minus p prime times x. That's the virtual bending moment. Again, if I look at x from the right, make sense? And the real curvature would be minus p times x over ei. Integrate that over 0 to L dx. And that would come out to be p prime p times L cube over 3 ei. And indeed, if I cancel off the p prime, when I equate those two, then I get the usual expression that we always get, pl cube over 3 ei. No surprise there. Let's take a look at the shear part of the energy now. Okay, so if I do want to account bending plus shear, then I would have to add ui. I would have to add ui from the shear contribution to the bending contribution. In that case, it would be equal to virtual shear stress. What would be the virtual shear stress? What? Yes. So the shear force diagram for the beam would be P prime, constant throughout, right? And divide that by cross-sectional area A. So I get P prime divided by A. That's the virtual shear stress. I'll stick in that factor, shape factor, and the real shear strain, what would that be? P over GA. So real force P, or real shear force P divided by GA. And I'll keep A dx here, integral 0 to L, cancel off one of the A's. And what we get is that this is equal to P prime P kappa divided by GA. And there's really nothing inside the integral, so it just becomes L, which implies that delta would be PL cube over 3 EI from the bending component plus P kappa L over GA. That makes sense where we got this from? All we are doing is we are adding UI bending plus UI shear. Maybe what I'll do is I'll write that here. If I do WE prime is equal to UI bending plus UI shear, then that gives me that delta is equal to the bending component plus the shear component. Okay. So you can see that it's relatively simple to apply this principle of virtual work even to complicated cases of shear deformation, which you were not able to do earlier, but it's just as easy to do as the bending deformation cases with principle of virtual work, right? All right, question, Miles?
Where would we find the cap factor?
It's usually given in tables, design handbooks. Usually it hovers around 1 for different types of shapes. Sometimes it's 5 over 6 or 4 over 3 or something like that. But yeah, okay. All right, so let's take a look at the same problem that we did for bending only, but now we are going to do all three: bending, shear, and axial. Okay, so in this case, the virtual bending, we already have the real response. The real response never changes. The virtual load would still be P prime being applied at that point, and the virtual, I'll just write that as here, same as real response, but scaled by P prime divided by 5. Make sense? So since this was a load of 5, I divide whatever value I have here by 5. And since we need to find the response for P prime, I just multiply it with P prime. So for example, here for shear force, if this was 5 kip, so I had a minus 5 kip shear force. If it was P prime, I would just take minus 5 times P prime over 5, we get minus P prime, right? So, so all we need to do now is to account for UI, well, let me start with WE prime as usual. WE prime, no surprises, it's always P prime times delta. And UI prime for bending, I'll write that. Would be exactly the same thing that we had from the previous example, so I'll just copy that expression. Let's see. Well, I'll just copy the final expression so I remember that. 5.33 10 to the 4 over EI, and P prime is still there. That was the expression for UI prime from the pure bending case. Now I will add to it UI internal energy, virtual internal energy due to shear. And how do I go about it? How do we sum up internal energy due to shear? Josh? Go ahead.
P prime over GA.
Yeah, P prime over A actually, because we are looking at for shear stress, right? So P prime over A, that's shear stress. We'll stick in that factor kappa, and the real would be P over GA. That's right. So P over GA. But P is actually equal to 5, so I'll use the value 5 here. So 5 over GA and times area of cross section dx integral 0 to 20. Do I need to account for anything else in the shear energy term? What I did was shear energy in this horizontal leg, right? Vertical leg does not have any shear in it, so indeed that will not contribute anything. If there was a real shear force and a virtual shear force in the vertical leg as well, you would have to add that up. April? Yes, I should, to be consistent, I do need to have a negative sign on both of them. So minus P prime and minus 5. Yes. And UI prime finally for the axial component, that would be this vertical leg. There's no axial component in the horizontal leg, so we can sum that up in a very similar way. Axial force, assuming tension is positive, it gives me P prime over A is the axial stress in the vertical leg, no need for kappa factor, times the real strain, that would be real force 5 divided by EA, and area of cross section dx integral 0 to 20, and there's no axial force in the horizontal leg. So if I sum these up, I get this is equal to 5 P prime kappa over GA times 20, and this guy is equal to 5 P prime over EA times 20. So now finally applying the principle of virtual work, WE prime is equal to UI prime bending plus UI prime shear plus ui prime axial, we get that delta C is equal to, simply cancelling off P prime from all these expressions, we get 5.33 10 to the 4 over EI, that was the bending contribution, plus 100 kappa over GA, that's the shear contribution, plus 100 over EA, that's the axial contribution. Okay, so no matter how complicated the structure gets, as long as you can draw shear force, bending moment, axial force diagrams, you can apply the principle of virtual work, you can calculate any displacement, any rotation you want. Okay, any questions on this?
Scroll down back to the
Sure. Okay. All right, so last bit of application of the virtual work method, not just shear force and bending moment, and not just shear force and axial force. We can account for torsion and even things like temperature change that I'll talk about in a bit. You could really not do those kinds of things with the methods that you learned from 371, right? So what's torsion? Right, it's a twisting type of an action where what you get, for example, if you have a cantilever beam and then you have an L-shaped extension of it where you apply this load, say upwards, then you can see that this would want to rotate like a wrench key if you have used that before, and the shaft of that wrench key comes under torsion. One face of that beam wants to stay put, the other face wants to rotate with respect to that. Right? That's very different from bending, very different from shear, very different from axial. We have this torsion. And this really is a three-dimensional effect. So that's why we did not have that as a deformation mode in the two-dimensional case. In two-dimensional case, really there is no third degree of freedom for you to rotate. So torsion really is a three-dimensional problem. Okay, let's see how we can account for torsional energy. You can imagine really that when I apply this load P, I can apply this equivalent load P right at this point. I could take this I could take this load, move it here, and apply a corresponding moment at that point. And that would be simply the same effect as a cantilever beam with a tip load that would undergo bending deformation. It would go shear deformation. But due to the torsional effect of this load, it would undergo additional torsional deformation, right? So you need to account for that displacement as well. And the logic is exactly the same that we had done for the shear, the axial, the bending. Find the torsional stress, torsional virtual stress. I'll mark that in red. As the torsional shear, well, let's just say torsional stress, and this is the real torsional strain. And we'll learn how to find those two things with these small notes that we have here. So to find these things, what we'll do is we'll take the small segment of that beam, blow it up right here, and you should be able to see that on the back face and on the front face there we have equal and opposite torsions trying to twist that beam. Very similar to a beam segment, if I have a M here, M plus delta M here, they are trying to bend that beam. In the same way we have T here, and in general we have T plus delta T, but just to keep things simple, we'll assume that the torsion is constant along the length of the beam. So T and T trying to twist the beam, which will cause this horizontal line that is along the axis of that segment to twist by an angle gamma. Okay, So you can see that this radial line here after twisting goes through, becomes that radial line. That's what this is showing. And if you really zoom into some sort of a element on that area, on that cross-sectional area, then you should be able to see that really the stress, the shear stress that the torsion causes. So for example, if I look at this cross-sectional face, and when I'm twisting it, then if you look at some small elemental area dA on the cross section, the stress on that cross section grows linearly as I go out from the center. At the center, the torsional stress is 0. Okay, and as I go out, the torsional stress increases linearly. So that's why we are writing sigma theta, the torsional stress, as some constant times r. R being the distance from the center. The small incremental force would simply be stress times area. So stress times area is the small incremental force. If I take the moment of that small incremental force, that would be R times dF. So that's sigma theta dA times R, and integrate that over the cross-sectional area. That gives me T. And if you just follow the logic, you will be able to see that sigma theta, the torsional stress, is simply equal to T, the applied torsional moment, divided by J. J is the polar moment of inertia that hopefully you all remember, and times the radius, or times the distance from the center, R. So with that, we can write this as T R times J. That's, and actually T prime, because that's the virtual torsional moment. The real torsional strain is calculated exactly the same way as the torsional stress. It's real torsional stress, and if I divide that by G, then that gives me real torsional strain. Any thoughts on why I divided it by G, not by A? Why did I? So when I want to calculate strain, right? So what I did was I first calculated stress, and then I divided it by G. Why did I divide it by G? G means there's some shear going on, right? So indeed, if you look at this small elemental area, and you imagine these two cross sections next to each other, one of those cross sections is going to try to shear against the other cross section. Right? So if you look at that small elemental area, that's really under shear, and so that's why we are dividing it by G, and I'll keep the rest of it as it is, dx integral over a 0 to L. And if you see, we have an r here, so integral r square dA, what is that? Integral r square dA. What is integral x square dA? It's Ixx, right? It's the second moment of area. Integral y square dA is Iyy, second moment area about the y-axis. Integral r square dA is really what J is. So r square dA and one of those j's cancel off, and what we get is 0 to L T prime T over J 1 over G times J dx. So one of these j's cancel off, but once again we'll write it just as it is. And if all of these things are constant, then ui due to the torsional effect is simply given by this expression. All right, so I've already gone 2 minutes over, so we'll stop here and then we'll complete this out on Friday. And on Friday we'll Hui, you can do a couple of examples on this also. So see you all on Friday.